In this video, we're going to talk about how to find the surface area of a particular surface. In my previous video, I talked about 3 different ways by which we could describe a surface: explicitly, implicitly, and parametrically. So in this video, we're really going to focus on surface area when the surface is described parametrically. And then in later videos, we'll talk about surface area when the surface is described explicitly or implicitly. So what's the setup? I have some surface like this one that I've drawn here, and I want to ask, what is its surface area? However, if I have described it parametrically, then what that means is that somewhere there is a UV coordinate system. And a region in the UV coordinate system that might look a little bit like this. It would start with U going between A and B, and V going between C and D. And the idea of a parameterization is that there is some map, some transformation of the two-dimensional region in the UV plane to this larger squiggly surface that I have. This surface that, for example, might live in 3 dimensions in some way. And then the way we would often write it down is that your parameterization R would be a function of U and V. And it would output some function f of u and v in the I hat, g of u and v in the j hat, and h of u and v in the k hat. It's the way you transform from the two-dimensional UV space, which is simple and easy to understand, it has just a rectangular region, to the more complicated geometry of this actual larger surface, a surface that might live in 3 dimensions despite itself being 2-dimensional. Now, we're going to solve this with integration. And the big idea of integration is always solve it for one small little piece and then add up over the entire region to get the answer for everything. So I want to imagine I've got a small little rectangle inside of the UV plane. This little rectangle may have a width, a change in U, and a height, a change in V. So then what I'm going to get is under the transformation that takes the UV parameterized space into what I'm actually talking about, I'm going to get something sort of similar over here. It's sort of like a rectangle, but more importantly, it's the transformation of the original rectangle, whatever that's going to look like on my surface. One way I can think about this is that in the original UV plane, a straight vertical line represented a constant value of U, and a straight horizontal line represented a constant value of V. And so likewise, the boundaries of this region, of this little sort of rectangular-like thing that I've written, represent boundaries where it's the transformation of something with a constant value of U, or the transformation of something with a constant value of V. Okay, I want to zoom in here. So let me take this little small sort of squiggly rectangle thing and just blow it up a little bit so that I have some space to do some writing on it. So I'll do a big version of that space, okay, something like this. Okay, so the first thing I'm going to do is I'm going to put in some point here. Maybe I'll just label it P just to indicate that's the point that I'm talking about. Now, I don't know exactly how the transformation worked, how it may have spun or twisted that original rectangle, but I'm just going to assume that this left-in edge is where you have a constant value of the V. That is, V is not changing along that edge, and that is, only U is changing. And likewise over here, I'm going to assume that this one is a constant U. It doesn't matter, it could be exactly the opposite, but nevertheless, we have this choice. So then I'm going to put in 2 vectors. This vector here is going to represent the transformation and the partial derivative of that transformation with respect to U. When you take a partial derivative with respect to U, that means that the other variable, V in this case, is constant. Similarly, I have another vector over here, which is the vector, the partial derivative of R with respect to V. Now, these vectors point in straight lines, but the actual underlying surface might be not a straight line. And so these are just going to be approximations, the same way that a tangent line is always just an approximation to a curve. But if we're zooming in far enough, then it's actually a good approximation, at least as long as our surface is sufficiently nice, and we'll talk about some of those conditions a little bit later. Okay, now I'm going to draw a third vector. I've got RU and I've got RV, so it's quite natural to create a third vector, and this is the vector RU cross RV. It's the cross product of these 2 vectors. Okay, that's good, but I want to have a stretching factor. The argument here is that This RU might be, for example, quite a bit shorter or quite a bit longer than the left turn edge. But if I have a scaling factor, so it's the exact same orientation but just changes in the scaling factor, this is the vector RU times delta U. It's much like saying the change in y is the derivative times the change in x. And likewise, I can have a scaling factor on the RV and get a vector RV times delta V. This vector is pointing in the right direction of these tangent vectors, but now it also has the length to be, well, not exactly the same as the length of the curve, but at least in the limit where the delta U and the delta V go small, it's going to be a good approximation to it. And similarly, I would get another vector that would pop up and be longer up here. That would be the RU cross the RV times the delta U and times the delta V. It's just the cross product of the other two green vectors. Now, here's the key. Here's the real magic. The length of a cross product is the same thing as the area of the parallelogram of the two vectors that form the cross product. So I can imagine that there's sort of a parallelogram here, and the area of this parallelogram is given by the length of the cross product. Okay, let's write that down. And then the argument here is that I don't know what the exact surface area of the original little portion of the surface was, but I'm going to approximate it. I'm going to approximate it by this little parallelogram that sits on it and has the property that the edges of the parallelogram are tangent in each of the two directions, the RU and the RV directions. And then because I can compute the area of that approximation, this little parallelogram, very nicely via the cross product, I have a good approximation for the underlying surface area. Okay, I can just do one little bit more of manipulation on this. I'm just going to make it the length of R of U cross R of V, and then I'm just going to bring the delta U, delta V outside of the norm here, just to clean it up in the full. And the purpose here is I am approximating the surface area of a little region who in the original UV space is shifting by amount delta U and delta V. And so I'm going to do the same trick we've done with integration anytime we've come up with a new geometric concept based on the same integration technique. Namely, I'm going to think of a limit as the delta U and the delta V's get small. Namely, I'm adding up all sorts of these little parallelograms. But I'm taking the limit as the delta U's and the delta V's get smaller, which means there's more and more parallelograms. And in that limit, it transforms into the definition of an integral. So my final formula is that the surface area is equal to, well, adding up a whole bunch of areas is going to give me a double integral of, well, precisely this object, the magnitude of R of U cross R of V. In the limit, the delta U and delta V going to 0, we replace them with a du and a dv, the infinitesimal versions of them. And then the u's can be assigned generically to go between an a and a b, and the v's generically between a c and a d. And that is our final formula. So basically, what we were able to do here, which is kind of awesome, is we were able to study the transformation and look at just a little tiny piece of the surface, which was well approximated by the length of this cross product. And we gave a geometric argument why that was a reasonable thing to do. And now I just got this integral formula. So if you know a parameterization, if you have a parameterization R of U and V, if you know what that is, well, this is just computational. Take a cross product, take a magnitude of that vector that you get out of it, and perform some double integral. If you can do that, then you can compute the surface area. So in the next video, we're actually going to see an example of this where we compute, perhaps for the first time in our lives, the surface area of a sphere of radius a and show that that really is going to be 4 pi a squared. And we're going to do it using precisely this formula.